the next chapter in communication. Sometimes a device like a sensor that is unable to communicate via one of the supported protocols, such as UART or I2C, is to be integrated. In this case, the entire protocol with all its rules and timings needs to be implemented in software. Maybe not the entire protocol is required, but only a subset of it, which then reduces implementation efforts. Literally, the developer is going to control the wires bit by bit, and hence a software implementation is also called bit banging. So what are we going to do in this chapter? We will have a look at proprietary protocols, such as the one-wire by Maxim. What are the advantages of that protocol? What are the disadvantages? In the end, what are the libraries that exist to support the development? Let me take the opportunity to clarify a myth. Here we see two popular temperature and humidity sensors, which use one pin connection to communicate: the DHT11 on the left and the DHT22 on its right. For small projects, the DHT11 is sufficient. If a higher accuracy or tolerance is required, then the DHT22 is an inexpensive alternative. I'm going to attach the datasheets for both of these to the lecture for more information. The myth is that the DHTs utilize the one-wire communication protocol. Though there are similarities when the DHT11 or DHT22 communication protocol is compared to the one-wire protocol, they are not compatible and have major differences. We are going to talk about those differences in this chapter. First, how are the temperature sensors connected? The DHT11 and DHT22 are pin compatible, so the connections are the same for both of them. Therefore, here is VCC, which can be 5 volt or 5.5 volt. This is the communication pin. This third pin is not connected, and C stands for not connected. And we have ground. There's a pull-up resistor between data and VCC, which is usually something around 5 kilo ohm. Personally, I use 4.7 kilo ohm, since those resistor values are much more common and cheaper than a 5 kilo ohm resistor. How does the DHT communicate through the one data wire? First, the line idles in a high state due to the pull-up resistor. If the master wants to check the humidity and temperature, it pulls down the wire and holds it low for at least 18 milliseconds. After that period, the master lets go of the wire and it recharges to a high state. Now there is a switch in the direction of communication, and from now onwards the DHT reports the temperature and humidity. The DHT pulls down the wire for 80 microseconds and lets it recharge for another 80 microseconds. Hence, the master knows that there is a temperature sensor present. Therefore, this part is also called the presence pulse. If the DHT is faulty, not ready, or not present, this pulse is not being sent. After the presence pulse, the communication starts immediately, and it is straightforward. The DHT pulls down the wire and holds it there for 50 microseconds. After that, it will let go and the wire recharges. depending on the time when the DHT pulls down the wire again, for instance here, A0 or A1 is transmitted. If there are 26 to 28 microseconds between letting the wire go and pulling it down again, A0 is transmitted. However, if there is a 70 microsecond gap between those two events, A1 is transmitted. That is quite easy to implement. The developer just have to count a time or the number of clock cycles between those two events. For instance, between this event and this event for A1, or this event and this event for A0. Since the events have to be measured in quite an accurate way, long ISRs cannot be used during the communication. Executing a long ISR might miss some events here and there. And that is how they communicate. As far as I am aware, this protocol is specific to the DHTs, and it is incompatible to the one wire as mentioned before. For a start, one wire has several command sequences, and the time frame for a bit to be transmitted, that is 0, or a bit that is 1, is the same in one wire. Here in DHT, the time frame varies depending on the value to be transmitted. Either it is around 76 to 78 microseconds, for instance, if a 0 is to be transmitted, or around 120 microseconds if a 1 is to be transmitted. In addition, and that is the most important difference, one wire is a bus and allows multiple devices to be addressed. Hence, it supports an addressing scheme. How does one wire work? Here we see two one-wire devices. On the left is the famous door access knob. The little metal piece on top of the blue plastic that looks like a button cell is a one-wire device. When it is connected to a one-wire master, they communicate to allow entry or not. Do note that there is no active power supply, so in that button cell shaped metal piece is no battery. A beautiful part is that one wire can not only transmit data through one wire, but also power to allow one-wire devices to operate for a short amount of time. Another example is an EEPROM shown on the left. It looks like a voltage regulator or transistor with 3 pins. However, it is a one-wire EEPROM able to hold 112 bytes in a pretty small form factor. A look into the datasheet of the EEPROM, and again, the datasheet is attached for more information, reveals that out of the 3 pins for the EEPROM, 1 is for the ground here, 1 is for the I/O or data right here, and the third one is not even connected. Same with the EEPROM in other packagings like the UCSP or the TCOC. In all 3 cases, only 2 pins are used. How does that work? Here is a small circuit diagram showing how the EEPROM is to be hooked up to a microcontroller on the left. The ground pin of the EEPROM is connected to ground. However, the I/O pin right here is connected to VCC right here through this pull-up resistor. Therefore, if the line I/O is not in use, it idles high, like the wire that we have seen earlier in the session about DHT or in I2C or even UART not too long ago. Since it is charged to the VCC level, it is used to power the EEPROM. However, when communication is commencing, in one point in time, the master is going to pull down the wire to the ground to transmit some data. So the EEPROM needs to have some sort of method to bridge the times when I/O is 0 to remain powered. Having a look into the EEPROM reveals how this is accomplished. We have here the I/O pin and the control, which then reads or writes the data depending on what the master tells the EEPROM to do. We can also see that there is a ROM holding a 64-bit long ID. More about that a bit later. The biggest part is on the top. It consists of a transistor and a capacitor. If the I/O line is unused and is idling high at, for instance, 5 volt, the capacitor is charged. If the I/O line fails to supply power because someone pulled the line down to the ground to write a logic 0 to it, the capacity in this capacitor is enough to bridge over that time period, and it keeps powering the device till the I/O line comes up again, like a small independent power supply in form of a battery. Since the capacitor steals or siphons off from the data line to deliver its charge when the data line cannot, this mechanism is called parasitic power, and that is how devices remain active. What about multiple devices? A major difference that I mentioned earlier when comparing with the DHT protocol. In this session, we talk about how one-wire devices communicate. The one-wire is a bus and allows multiple devices, such as the EEPROM mentioned previously, to communicate and to draw power from a single line as shown in this figure in green. That means the master or MCU needs a way to address each of those devices individually. To do so, each of the devices has a unique 64-bit ID programmed into a read-only memory. Since this ID can never change, and it is unique not only in the bus, but on the entire planet. Remember in I2C, for instance, the address was to be unique only within the same bus, but it can be repeated on a global scale. Not so in one-wire. The ID is divided into 3 parts. The 8 most significant bits contain a family code identifying what kind of device it is. This is followed by a 48-bit serial number and ending with an 8-bit checksum. I am attaching a link into the resources folder to an online calculator to compute the checksum for arbitrary addresses. What else is important about the one-wire communication? Yes, it uses one wire, so the communication is half duplex. Unlike I2C though, in the entire bus there can exist only one master communicating at speeds of 15.4 kilobit per second, or in an overdrive mode even faster, at 125 kilobits per second. While this is slower than what we are used to and compared to the other communication protocols that we had so far, the cabling efforts are a lot lesser. And in addition, considering for instance the EEPROM that we had earlier being able to store 112 bytes, how long does it take to transfer those bytes? Interestingly, regarding the maximum distance that the devices can be apart, there is no definite answer. It depends on the weight, The weight is a way to measure the overall capacitance of the bus. It is influenced by the wire length, number of devices, if they draw parasitic power, how far they are from the bus, and much more. For instance, if this EEPROM moves down a little bit, this wire connecting the EEPROM to the bus becomes longer, and hence, with the increase of the distance, the overall weight increases as well. That means the topology does not need to be a bus, but it can also be a star, for instance, like this one. Many more constellations are possible, and as usual, you will find more information in a link located in the resources folder. But how do the devices communicate? In this session I will show how the one-wire communication works. Since one wire is half duplex, we have either the master, that is the microprocessor, communicating with a slave, such as an EEPROM, or vice versa. To the entire chapter, I will use the blue color to indicate that the master is actively driving the wire, and red if that is the case for at least one of the slaves. If the line in a timing diagram is black, no one manipulates the wire, and it returns to its high idling state. Let's have a look at the case if the master sends a 0 to the bus. First, it pulls down the wire and holds it there for 60 microseconds. The protocol states that the slaves will sample the value of the line at the 15 microsecond mark. The line is here in red to indicate that the value is sampled by the slaves. However, if the master wants to transmit a 1, it pulls down the line again, as we see here in blue. But then the line is released way before the 15 microseconds mark. So the line returns to its high idling state. And when the slaves read the value of the line at the 15 microseconds mark, they will read a 1. If the capacitance or the weight of the bus is too high, the line will not return fast enough. To compensate, the master could release the line sooner, but some of the slaves might not have recognized that someone is pulling down the line to 0 in the first place. So the timings need to be matched. As you can see here, no matter if a 1 or 0 is transmitted, the duration is always the same, 60 microseconds, not like in a DHT protocol. If the slave returns data to the master, like the EEPROM reads data from its memory banks and sends it back to the master, again, the master pulls down the line. But then it lets it go. The slave recognizes this event and takes over right here. If it wants to send a 0, it holds down the line for the remaining time, or just does not do anything and the line returns to a logical 1. Now it is the master's turn to read the state of the line at the 15 microseconds mark here in blue. Taking a step back, how does the entire protocol look like? First, the master initiates communication with a reset pulse, which lasts between 480 and 640 microseconds. All the slaves reset their communication interfaces and return them to a known state. After that, the master releases the wire. Now, the slaves send a presence pulse lasting between 60 and 240 microseconds. To the master, it is unknown how many slaves are there in the system. It just knows that there is at least one slave present. Again, a step back. Here we have the reset pulse by the master and the present pulse by the slaves. Now everybody in the bus is poised and ready to communicate. The next will be the command ROM sequence. There are quite a few commands available. Do note that those are not the commands for the slaves, but commands concerning the entire bus. For instance, there is a read command, which just reads the ID from a single device, or the skip command used if there is only one slave on the bus, and hence the 64-bit address that is transmitted after the command ROM sequence can be omitted. Another one is the Search ROM command, which identifies which IDs are there on the bus, and the master uses that command to build a table of unique IDs of all the attached devices. The command sequence is followed by the ID if a slave is to be addressed. Then the device command. These commands are specific to the device. To stay with the EEPROM example, supported commands might be read or write the memory from a particular address, or clear everything, etc. Another one-wire device, such as the doorknob, will have other commands that it supports. After the device command, either the slave or the master will communicate. For instance, the data is read from the EEPROM and delivered to the master, or the master writes to the EEPROM. After the communication is complete, both parties withdraw from the bus and it returns to its high state till the communication restarts from the beginning. In this session, I will show how one of the commands for the one-wire bus works, and that is the Search ROM command. This command will find all one-wire devices connected to the bus in multiple iterations. Here we see the first iteration. Let's say there are 4 devices connected to the bus, excluding the master. The last 4 bits of the ID of each of the devices are shown here, while I skip the remaining 60 bits. The timing diagram shows where we currently are in the communication protocol sequence. As you can see, the master already sent the reset pulse, and the slaves replied with the presence pulse in red. After that, the master issued the Search ROM command, whose bit sequence is F0 in hexadecimal format. Now, all slaves are in a Search ROM command state with an index pointing at the least significant bit of their respective ID. First, the master pulls down the wire to its logic 0 level to indicate the start of the transmission of 1 bit. Since all slaves are in a Search ROM mode, all of them write their current LSB of the ID to the bus. Hence, devices 1 and 4 write 0 and pull down the bus to its logic 0 level, while devices 2 and 3 do not do anything since they want to write a 1 to the bus. However, a pull down and connecting the wire to the ground is stronger than the pull-up resistor. Thus, a 0 is read by the master after 15 microseconds. This data is stored in the master. The next step in the Search ROM sequence for the slaves is to write the complement of the currently considered bit of the ID to the bus. When the master pulls down the wire to transfer the next bit, this time devices 1 and 4 want to keep the wire in a high idling state. However, devices 2 and 3 pull down the wire to the logical 0. Now, the the master compares the current reading and the previous reading. Both of them are 0. Hence, the result is interpreted as at the current bit location, some slaves have a 1 and some have a 0. The master does not know how many slaves are there on the bus, nor how many of those have a 0 or a 1 at this position. It has to make a decision in the third step, and it writes the bit value onto the bus with what it would like to continue. In this case, it is a 0. All slaves read the third value. Those slaves whose bit does not equal this red value drop out of the communication and do not participate in the search ROM command sequence anymore, but remain silent till the command sequence completed. Those slaves which are still active move the index up by 1 position, here marked in red, and the master restarts. Again, first the master pulls down the wire and the slaves write the bit value of the second bit onto the bus, here 0, which is read by the master. Then the slaves write the complement of that bit value onto the bus. Since the ID of both slaves is 0 at this position, a 1 is written to the bus. The master again compares the previous reading, which was a 0, and this reading, a 1. Hence it knows that there is at least one slave, but it could also be multiple ones on the bus, and all of them have a 0 at this position. Again, the master decides how to continue, which is quite trivial in this case, since there is no choice other than writing the decision continue with 0 onto the bus. All slaves have a matching bit and no one drops out. Let's consider the third bit. It is the very same situation that we had when the least significant bit was considered at first. In both cases, when asked the slaves to send the third bit and its complement, 0 is read from the bus by the master. Hence it knows that there are still at least 2 slaves available. At least one of them has a 1 as third bit. Again, the master transmits its decision how to proceed, and slaves that have a 1 at the third position continue with the search ROM command, while all other drop out. Then the master moves on to the fourth bit. Now there is only one slave left, which is the only one that responds to the next bit requests by the master. Hence, there is no ambiguity anymore, and the considered bit and its complement counterpart are always correct. This goes on for all 64 bit, after which the run is completed. By now, the master identified one wire device that exists on the bus. But there are more, and there are 2 situations in which the master had to decide how to proceed. Hence, the master repeats the search ROM command, but decides differently if possible. For instance, here it decided to continue with 1s and device number 1. Now the master decides to continue with devices that have a 0 here, identifying device number 4. Alternatively, the master can decide differently at this position and go through the branch identifying device 2 and 3 in this iteration. To identify all devices, in total 4 iterations of the search ROM command are required. Since there is no hardware support for the 1 wire in the ATmega, there are 2 options. First, a dedicated chip is integrated into the system that is able to translate between the one wire and the supported protocol such as I2C. Or second, the entire functionality needs to be implemented in software. For instance, the protocol says that all one-wire devices must understand the search ROM command. But other commands might be optional, such as the overdrive command to increase the data transfer rate. If another IC is out of the question, maybe due to the wiring, power, cost or space constraints, a software implementation needs to be considered. Now, the transfer rate is quite fast. How can the DHT or one-wire protocol be implemented? If the developer is lucky, someone else was in the same situation before, solved the problem, at least partially for the processor in the system, and released the code as open source. There are a few libraries out there which can be tried on the ATtiny, a smaller brother of the ATmega 328P, which we are going to have later in the course. Especially the DHT is very popular and numerous library implementations exist. The situation is slightly more difficult for the one-wire protocol. It is not as forgiving since the timings are tighter compared to the DHT protocol, and smaller processors are not able to sample the data at the required timings. Hence, quite a few optimizations are required to make it work. There are some libraries available in which the ATmega 328P can mimic a master in the one-wire bus. If the ATmega is a slave, then the developer might need to hit the keys and program it by herself. Let me know and shoot me an email in case you come across a slave library for the ATmega, for instance. If the software implementation does not work, an oscilloscope is a powerful tool to track down any timing violations. Make sure that the sample rate of the oscilloscope is at least double, better 4 times the frequency of the signal to be sampled. As a rule, a more sensitive oscilloscope is always better. However, they become costly very fast. Usually, the small ones start at around 150 to 200 US dollars with no upper limit. Nevertheless, in the exercise, you have to implement the DHT protocol, and I provide the binary to convert the ATmega into a simple oscilloscope. Please note that this oscilloscope is by no means comparable to the commercially available ones. Its sample rate is around 76 kilosamples per second. Even the cheap oscilloscopes have multiple megasamples per second. 76 kilosamples per second means that this ATmega oscilloscope takes a sample every 13 microseconds, which is too slow to debug one wire. However, for DHT, it is just enough. I'll show in the next session how to use it. It is not as comfortable, but you are free to improve it, and it does not set you back hundreds of dollars. In the chapter about ADCs later in the course, I'm going to discuss how to implement such an oscilloscope. For now, the ATmega oscilloscope serves its purpose. Let me show you the setup that I currently have. This is my DHT11. This is VCC. The second pin is the data pin. The third pin is not connected, and on the most right side I have ground. Here I have my VCC. This is ground as well as this one, so I have a common ground here, and this is my 4.7 kilo ohm resistor. That means this is the data line going into pin 6 of this Arduino. Then you can see here the orange wire. The orange wire goes into A0, so this ATmega is my ATmega oscilloscope. Okay, let me put it in. So we can then measure the temperature. I have inserted the DHT11 with this voltage pin on the left and ground on the right, and the second from left is my data pin. Now let's head over to the VirtualBox image and see if the temperature and humidity can be read out from the sensor. Let's head over to Qtcom to see if the temperature and humidity is reported. There are currently two ports. This is the ATmega that reads out the temperature and humidity, and this is the ATmega that I use as a ATmega oscilloscope. So let's read out the temperature and humidity. The baud rate is 115,200, 8 data bits, 1 stop bit, and no parity. Let's see if it works. As you can see, the relative humidity is currently around 38% and the temperature is 23 degrees Celsius. This program comes from the standard Arduino DHT11 program that I'm going to attach as a link to the lecture. Now let's head over and see how this protocol actually works. For that I open a terminal. Let me increase the font size a little bit. And we head over to course, one wire. There are two directories, digital oscilloscope, which can read the value on a digital pin, so it's either 0 or 1. The advantage is that this digital oscilloscope has a higher frequency of sampling, so it has a higher sampling rate. This oscilloscope is non-digital, so it's an analog oscilloscope, but it's a little bit slower. And the sample rate is 76 kilosamples per second, roundabout. That means between two values that are reported are around about 13 microseconds. There are several implementations, so I'm just providing the hex files here, because this is actually an exercise later in the course where you have to program this oscilloscope. I'm providing several oscilloscope implementation and several baud rates. So for instance, this one is 500 kilobaud, this one is 115200 baud, and the highest one is 1 megabaud. Depending on your Arduino and on the circuit board that you have, this 1 megabaud might not be supported, and hence you have to take a little slower ones. Obviously then the sample rate will also decrease because the values cannot be transmitted fast enough. Having a look at the makefile, it just contains the upload. Here you can choose which one you would like to upload by removing the comment, and then it just contains the upload sequence. Alright, so once you uploaded the program into the ATmega, probably you should start with the 1 megabaud because the sampling rate is the highest. And how to get the data out. For that you have to use a helper program, which are here. This is basically just a program that converts the binary data transmission into an ASCII number that we need to plot the data. So for instance, binary all zeros except the least significant bit is set to 1 is converted into a 1 but in ASCII. And how to use it? All the commands that I'm covering here are also in this readme.txt. Unfortunately, Qtcom does not allow to set the baud rate to 1 megabaud. It does not accept the input in the settings. Therefore, we have to use a little trick, and everything is mentioned in the readme.txt. First, I have to use stty with the port that I'm considering. The baud here is, for instance, 1 megabaud. This means 8 data bit and 1 stop bit, and then we have several settings here which I don't cover in this lecture. So let's execute this command. I'll just copy and paste it. Please adapt the port number to the port number that you have and the baud rate to the binary that you have uploaded into your ATmega. Now the port is set, and we can just display it by removing all the settings. So if it doesn't work, you can execute this multiple times, and for instance, if the machine reboots or so, then the setting will be put back to 9600 baud, so you have to re-execute this command. Then I'm using this helper command. This helper command actually opens TTY ACM 0, so there's a parameter that I have to give here, and how many samples do I want to collect. This helper program then reads out the binary data stream coming from the Arduino and converts it automatically into ASCII, so it's one single way. Otherwise, you can just open the port and log the data, the binary data, into a file. And there is another helper program, just bin to CSV, without the TTY, which takes as an input a file name. So you can see it, for instance, here. So if STTY does not work, you can also try out Minicom. Minicom also allows you to put 1 million here, but I have personally not that good experience with Minicom, and hence I haven't tried it any further. This probably just depends on the setup that I have here. You might have better luck with Minicom compared to STTY. So if STTY does not work, just try out Minicom once. Minicom can then also capture the file. However, that is then the file that comes as a binary stream from the ATmega, and the helper function then converts the binary data stream in this file into a ASCII file. So it's basically a two-step here, whereas here everything is in one single step. That's why I prefer it this way. Okay, let's check if the settings are still there. Perfect. And now I collect the data. So I just copy and paste it again. But I want to have more samples here, so I put 1 million here. And then I started once the ATmega asks for the temperature. The interval that it asks for the temperature is once every 5 seconds. So you have to time it a little bit so that you don't collect megabytes and megabytes of data. Or you just let it run till 1 million samples. You can interrupt the collection of data by pressing down Ctrl and C at the same time. Okay, let's start. So I saw that the Arduino reported once the temperature. So I interrupted it with Ctrl and C. That's why this character is printed here. Let's have a look. So I have this log file here, and you can open it. This one is the sample number, and this is the data that has been read from the line. 255 is the highest and 0 is the lowest. And how many samples do we have? So we have here 363,383 samples, and maybe it ran like for 5 seconds or so. So quite a lot of samples. The time difference between, for instance, this sample and this sample is 13 microseconds. So every time it's 13 microseconds. Okay, let's plot it. For that we are using an open source program called GNUPlot. It's pre-installed on the VirtualBox image. You just invoke it, GNUPlot. And we want to plot something. We give it a file name, that is in this case log.txt, and I want to plot it with points and with lines between the points. So I write lines, points. But this is just optional, so you can just hit enter after this. It takes a little bit. So these are all the values. So the highest, as you can see, is 255, and somewhere we have values that are different from 255. Make it a little bit bigger. Since there are so many values, it's a little bit slow. So patience is required. To zoom into this area of interest, hold down the right button, hold it down while you drag a box. So as you can see, it's a little bit slow. It gets faster the lesser points it has to display. And once you have the box, release the right mouse button and click the left one. Alright, so we can zoom even further into this, and you can see it becomes faster. So here's our line idling high, and here you can see the reset pulse. Sometimes there is a glitch, so this point here, for instance, is a very short glitch that is probably not there on the line. That's why this is just a small ATmega oscilloscope, so these things tend to happen. Just ignore them. And here we see the data transfer actually. So this is even more interesting. The reset pulse is here from the master, and then the master released the line. So it recharged, and then the sensor pulls it down for the presence pulse. So this is supposed to be 80 microseconds, and this is supposed to be 80 microseconds. Then we have several up and downs here, and the DHT protocol says if the idling phase is between 26 and 28 microseconds, a 0 is transferred. This is probably in this case. So this is probably a 0 here. And if it's 70 microseconds, it's a 1. So you can see that this time here is a lot larger than this time. Zooming a little bit further into the plot, we see that there are actually little pluses here. These are the points that are being measured. We said earlier that currently we sample at around 76 kilosamples per second. That means the time difference between this point and this point is 13 microseconds. And these are the lines that you get when the plot is plotted with lines, points. So the points are marked in the log.txt, and consecutive points are connected by lines. The time difference between this point and this point is 1, 2, 3, 4 into 13 microseconds, which is equal to 52 microseconds. However, this should be the 1 and this should be the 0. So this one should be 70 microseconds and this one should be 26 to 28 microseconds. And this is the disadvantage of the ATmega. 76 kilosamples per second is very low compared to oscilloscopes. We can for certain say that the line was up for 13 microseconds. However, we do not know exactly where it went down. For instance, the next point here might be somewhere here, down there, and the previous point of that point might be somewhere here. So between this point and this point, the line went up. It can have happened here, for instance, and it could have gone down here, for instance. So the total width of this bar is somewhere between 1, 2, 3 into 13 microseconds and 13 microseconds. So the maximum of this bar could be 3 into 13 microseconds, which is 39 microseconds, and the minimum is just 13 microseconds. That's what we see. So there's quite a large difference between these 2 points. We know it has to be something between 26 and 28 microseconds, because this is what the protocol dictates, but we don't see it. Therefore, the ATmega oscilloscope is not really designed to get protocol timings right. However, it helps a little bit to check if the software implementation is correct. For instance, if the present pulse comes, if it's long enough, and roundabout if the data, that means the zeros and the ones, are transmitted properly. And this is already a great help. So that is about the resolution of the oscilloscope. As you can see, faster sampling times are always better. However, for the ATmega, 76 kilosamples is the maximum it can do. Okay, zooming back, what else did we get? So this is our presence pulse. Then the DHT transferred is 0, 0, 1, 0, 0, 1, 0, 1, 0, 0, 0, 0, 0, 0, 0, 1, 0, 1, 1, 1, 0, 0, 0, 0, and 1, 1, 1, 1, 0, 0. If you count now the numbers of spikes that we have here, there should be 40 spikes for 40 bits. The first 8 after the presence pulse here is the humidity. This is 1, 2, 3, 4, 5, 6, 7, 8. If I convert this binary sequence into hexadecimal, then probably I get something like 38 or 39. So let's see. Binary, it's 0, 0, 1, 0, 0, 1, 0, 1. Are these 8? So this is present pulse 0, 0, 1, 0, 0, 1, 0, 1. So it's 37. Let's check what the DHT reports. Ah yeah, 37, 38. So in this time when it asked for the temperature and the humidity, 37 were reported. Then it follows a few zeros. So we have here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 zeros. The first 8 after that, so from here to here, these represent the decimal part of the humidity. The DHT11, however, does not have the resolution for decimal part. So the maximum resolution for the DHT is 1. So it can distinguish, for instance, 37% and 38%, but not 37.5 or 37.8. That's why these bits are always 0. Then the temperature follows. So we have here 1, 2, 3, 4, 5, 6, 7, 8. Up to here is the humidity. Then the temperature is 0, 0, 0. So let me type it in. 0, 0, 0, 1, 0, 1, 1, 1. 1, 0, 1, 1, 1. This should be 8-bit. And we have 23 degrees here. So this is the temperature. Same here. The next 8 zeros are for the decimal part. But the DHT11 does not have any decimal part. The resolution is plus minus 1 degree. That's why the next 8 bits are always 0. 1, 2, 3, 4, 5, 6, 7, 8. This is followed by a checksum. So the checksum is very simple to compute. It's basically the sum of all fields that we have. So this is the integer part of the humidity plus the decimal part of the humidity plus the integer part of the temperature plus the decimal part of the temperature. That means we had 23 plus 37, which comes to 60, and binary wise, so it starts with 2 zeros, then 4 ones, and 2 zeros again. 1, 2, 3, 4, 5, 6, 8. This belongs to temperature. 1 0 1 0. These are these two zeros. Then 4 ones, 1 2 3 4, and 2 zeros. And then the line idles high again. And that's how it works. If you would like to zoom out a little bit, so you can press here this magnifying glass, and if you want to see everything again, then here's a magnifying glass with a little 1 inside, and then it displays all values in that log.txt file. If you want to see other communication protocols, I collected some. So we have here the DHT11 that I just showed. Then we have here a DHT11 simulator. If you don't have a DHT11 sensor, you can use this program here that I prepared. It converts an ATmega into a temperature probe which supports the DHT11 communication protocol. And you have to connect pin D2 or the Arduino pin 2 to read out the temperature. The temperature is not that accurate. Don't worry if you read temperatures in a range of, for instance, 80 degrees. The temperature node of the ATmega is not calibrated, and its accuracy varies from chip to chip. I disconnected the DHT11 and just connected the temperature probe of the ATmega. And these are the readings. It doesn't have any humidity sensor, so it's always 0. And now we measure, for instance, 69 degrees. Don't worry if the number is off by a lot. The temperature sensor is not calibrated. The ATmega temperature probe, if you want to use it and want to check out if the number is correct, this is transmitted here. Now we have 70 degrees. You can do so using QtCom again. This time it is USB 1, so I just connected it. And it reports it at 57600, 8 data bits and 1 stop bit, but in hexadecimal. The temperature that is reported is here. So 46 hexadecimal should be 70 degrees in decimal. And there we have it. So in your implementation, if it shows 46, 70 should be printed out. Right, this is just a different presentation. This is decimal and that is hexadecimal. These other numbers, they are not that important as of now. That we will handle in the chapter about ADC later in the course. Alright, now you know how to connect a DHT. You can use either DHT11 or DHT22. If you don't have either of them, you can use the program that is supplied in a directory temperature DHT11 communication. Then you also have the luxury of checking if your implementation is correct by checking what the Arduino or the ATmega is reporting through the UART interface. In addition, I just showed you how to plot things. So we have the log file here that I'm going to delete, but you can regenerate it. Here are some examples. This is, for instance, read out from the temperature probe on the ATmega, and then how to plot it. If you want to repeat a command, you don't have to retype it. You can use either replot, it then plots it again, or you just use the key arrow up, so you can go through the commands that were there previously. To exit GNUPlot, just type exit and you're back on a normal prompt. That's all what I have for you today. Have fun in the exercises. If you get stuck somewhere, I add hints and tips usually, so you can check your code if you made any common mistake. And once you're done with the exercise, I see you in the next chapter about the next communication topic that I prepared for you. As a summary, what did we do in this chapter? First, we talked about the DHT protocol and established that this protocol is incompatible to the one-wire protocol. Depending on the bit value to be transmitted, the frame length changes. It also supports only a point-to-point connection and hence does not require any addressing. In contrast is one-wire, which is a bus system supporting one master and multiple slaves. The slaves can communicate and draw power through the same wire, simplifying wiring efforts. This is called parasitic powering. Each of the one-wire devices has a globally unique 64-bit ID, including a checksum. This ID serves as an address in the bus. To find all devices on the bus, the Search ROM algorithm is used identifying one slave device with every iteration. What will be the topic of the next chapter? Only one more communication protocol is left, USI. Technically, USI is actually not a communication protocol. What it is, we will see in a bit. Please have a look at the exercises. I'll start them by giving a short demonstration about how to use the ATmega oscilloscope. In the exercise, we will have to implement the DHT protocol by bit-bagging a pin to a DHT humidity and temperature sensor. You can use one if you have one. If you do not have one, you can use a second Arduino and flash the provided DHT program. It will behave like a DHT sensor and reports the temperature. More about how to report a temperature without a temperature sensor in the ADC chapter. For now, please head over to the exercise. And then I'll see you again for the lecture about USI in the next chapter. See you in a bit, and thanks for watching.